السلام عليكم. نتمنى تكونوا بخير على احسن حال، ومرحبا بكم في هذا التمرين في مادة الفيزياء والكيمياء للمستوى الثانية بكالوريا المسالك الدولية خيار انجليزية. فهذا الدرس، هذا التمرين هذا كيندرج في درس ديال الكواكب والأقمار الاصطناعية. اوكي، دونك غادي نقراو التمرين ونقراو الأسئلة، نحاولوا نهزوا المعطيات ديالنا، نديروا لهم يعني هايلايت، وهذا لتفادي ضياع الوقت أثناء الامتحان. ونبداو على بركة الله. Part 1: Study of the motion of an exoplanet around its star. So an exoplanet is a planet that orbits, نساو هنايا واحد that orbits a star other than the sun. يعني an exoplanet يعني واحد بلانيت ما كتنتميش يعني المجموعة الشمسية ديالنا، وهي كتدور حول يعني نجم آخر، يعني كينتمي لمجموعة شمسية أخرى. In the last few years, astronomers have discovered thousands of exoplanets by using sophisticated tools and techniques. Mu'ara is a star, its symbol S, located at approximately 50 light years far from our solar system. 4 exoplanets orbit around Mu'ara. This exercise aims at determining the mass of Mu'ara using the Newton's second law and the Kepler's law on one of these exoplanets. Its symbol is B. We are going to determine its mass using Newton's second law and Kepler's law, as we have seen in the course. So the star S is a uniform spherical mass. The exoplanet B follows a circular path and its dimensions are negligible. So the exoplanet B follows a circular path. Donc déjà عطاونا هذا المعطى بمعنى the trajectory is circular، déjà عطاوها لينا، and its dimensions are negligible. هذا كيعني بأن distance between the sun أو the star and Mu'ara يعني كبيرة بزاف، is way bigger compared to their radius. هذا هو المعنى ديالها. There is only the universal gravitational force acting on the exoplanet B by the star S. هنا كيقولنا بأن القوة الوحيدة المطبقة من بيناتهم بجوج ألا وهي قوة التجاذب الكوني. We study the motion of B in a frame of reference linked to the center of the star assumed غالينيا. هنا كيقولنا بأن ديجا هما حدوا لنا frame of reference اللي هو linked to the star to the center of the star، يعني في هذه الحالة heliocentric، ولكن heliocentric ديال هاد star هادي. So given gravitational constant G is equal to 6.67 times 10 to the power minus 11 SI units. The radius of the trajectory of B around the star is, so this is the radius, and the period of the trajectory of B around the star is TB is equal to 5.56 times 10 to the power 7 seconds. The period is the duration at which the exoplanet Mu'ara revolves around the star once. So question 1. Write the expression of the magnitude FSB, the force that S acts on B, of the universal attraction force exerted by the star S of the mass ms on the exoplanet B of mass mb. And we have to be careful as to abide by these notations. Okay, so we need to use the notations of the exercise. So question number 1. Okay, so they want the magnitude, so the magnitude of the force that S acts on B, and we know that the magnitude of the gravitational force is G, gravitational constant, times the mass of the two objects. So we have mb times ms. Over what is the distance between them is RB, so over RB square. So this is the expression. Now, question number 2. By applying Newton's second law, 2.1, show that the circular motion of the exoplanet B is uniform around the star. So, by applying the Newton's second law, we are going to use Newton's second law in all these three questions, 2.1, 2.2 and 2.3. Okay. So ملي كيكتبوا لنا هنايا السؤال الثاني ومن بعد يفرعوا لنا السؤال الجزء 1 وجوج وثلاثة، وكيكتبوا لنا هنايا في السؤال جوج بمعنى by applying the Newton's second law. هذا يعني بأن هاد القانون الثاني نيوتن غادي نطبقوه، غادي نحتاجوه في الأسئلة بثلاثة يعني. So 2.1 show that the circular motion of the exoplanet is uniform. بمعنى غادي ديجا قالنا بأن الموشن is circular. اللي غادي نحتاجو نبينو فقط هو أن the motion is uniform، بمعنى the velocity is constant. Okay. Since we are going to use Newton's second law, of course, we are going to follow the steps. So the first step is the studied system. So the studied system in this case is the exoplanets. The forces, gravitational force, S on B, which is centripetal. وبالفعل إذا مثلا كانت هذه هي the star S، كان عندنا مثلا this is B, the exoplanet, and let's say that this is the trajectory. Okay, so the force will be like this. Okay, centripetal. We study the motion of the system in a frame linked to the center of the star, assumed Galilean, in a Freinet base. So we study the motion of the system in Freinet base. In Freinet base, so غادي نسميو Freinet base B U N. So B is this, the other vectors, U is tangent and N is normal, like this. So applying Newton's second law, as I know, Fs on B is equal to mb, the mass of the exoplanet, times Ag, the acceleration of its center of inertia. It gives us G mb ms over rb squared, which is equal to mb times, so this force is along the vector n, which is equal to mb times h. Okay, and we are going to name this equation 1. So projecting equation 1 onto the axis BU gives, so this gives 0, which is equal to, because this vector is along n, it has no component along the u vector, so it's 0, which is equal to mb times at, and we know that at is equal to dv from dt. So this is from the first lesson in mechanics, Newton's laws. Okay, so which is equal to mb dv over dt. So from this we conclude that dv over dt is equal to 0, which means that the velocity is constant, and this means that the motion is uniform. And that way we have demonstrated that the motion is uniform. Now, question 2.2. Establish the Kepler law, the Kepler third law, t square over r cubed is equal to k, where k is constant. So establish بمعنى نبرهن، يجب أن نبرهن. So 2.2. Okay, so to prove this, the third law, so we need to project this equation onto the other axis. So projecting equation 1 onto Bn. So this gives G MB MS over RB square equal to MB times AN, which is V square over RB. And now نكتب بين قوسين AN is equal to V square over RB. Okay. Again, this is from the first lesson in mechanics. So we are going to simplify MB with MB and this square with RB. And the result is V square is equal to G MS over RB. So we are going to name this equation 2, and we are going to return to it later. So we know that V is equal to RB omega. The linear velocity is equal to the radius of the circle times the angular velocity, and أولى with omega being equal to 2 pi over t, which is the orbital period. So V is equal to RB times omega, which is equal to RB times 2 pi over t. Okay, we have replaced omega here with its expression. Okay, so V square will be equal to 2 pi square RB square over t square. And we are going to name this equation 3. So obviously 2 is equal to 3. 2 is equal to 3 is equivalent to G MS over RB being equal to 2 pi square RB square over t square. So rearranging this equation gives us t square over RB to the power 3 is equal to 2 pi square over G MS. So G is a constant, MS is a constant, and 2 pi is a constant. So this is equal to K, which is equal to constant. And now, by now, we have proven that this equation is constant. Okay. Now, for the last question, 2.3, determine the value of the mass MS of the star. So from the start, the aim of this exercise was determining the mass of mu r. So determining the mass of the star. So we have this equation, we have all the data, okay? We can calculate ms. So we can name this equation 4. So from equation 4, ms is equal to 2 pi square times rb to the power 3 over t square over g. Numerical application, ms is equal to so 4 pi square times rb, which is 2.24 times 10 to the power 11 to the power 3 over t, which is 5.56 times 10 to the power 7 all squared times g, which is 6.67 times 10 to the power minus 11. So calculating this yields this value, so 2.15 times 10 to the power 30 kilograms. So the mass of this star is this, okay? So it's reasonable because the mass of our sun is equal to 1.98 times 10 to the power 30 kilograms also. So the same order of magnitude, okay? هذه نهاية هذا الفيديو، نتمنى تكونوا عندكم استفدتوا، وإلى فيديو لاحق إن شاء الله.